Hello, welcome to the presentation of my paper on realizing stateful functions as service in serverless edge networks, state propagation. This is a joint work with Marco Conti and Andrea Passarella. Serverless is a mature technology in the cloud ecosystem, very often used as a synonym of function as a service. In serverless, the developer writes a function like the one that is depicted in the slide, a simple one. This one uses Node.js, for instance, which is then deployed into the data center of a function as a service provider. Then the function is run inside containers, which are scaled up and down depending on the demands from the users. So the users can invoke those functions. So in this simple example, they invoke f with x, for instance, x is 5, and they get back the result. So in this case, the result will be 5 times 5, which is 25. As many instances as needed are spawned as containers, and this is done automatically. So the key advantage for the developer here is that they do not need to care or understand what happens for enabling the scalability of the service, and they can focus on writing the code alone. On the other hand, from the point of view of the users of the service, everything is transparent. They simply invoke those functions, they provide input as function arguments, and they get back the result that they want. Serverless has many advantages, such as flexible billing, infinite scalability, reduced time to market, but it also has some known issues, such as high tail latencies, unpredictable delay response in general, and difficulty in troubleshooting if something doesn't work as expected. However, in this presentation, we will not discuss those pros versus cons, but rather we focus on one implicit assumption of serverless. In serverless, basically every service provider assumes that the functions are stateless, meaning that they only provide a given response, a given return value based on the input arguments. They do not share or keep a state with the application that is invoking the function. The picture illustrates at a very high level the architecture of a serverless system. So we have a load balancer, which is on the cloud. So all the users in the world only see a single endpoint for the service, and the load balancer dispatches the function invocations towards the many instances of the containers that run the function. When the function runs, it can access the state on a distributed storage, which is also hosted in the same data center. And if the function also modifies the state, then it puts the updated state in the same storage repository. Everything is fine as long as we are talking about a data center in the cloud. But what does this architecture even mean when we are talking about edge networks? An edge network is a network where the computer resources are distributed across many nodes with smaller capabilities compared to the servers in the data centers. And these edge nodes may also cover a very large area, also on a geographical distance. So you don't have a single entry point for the load balancer. You don't have an easy way to implement a distributed storage system, and you don't have a way to access that storage system if you do it from each and every edge node in an efficient manner, also because the edge nodes may have limited network connectivity. Function as a service is used as a synonym of serverless, and implicitly it assumes that all functions are stateless. However, not all functions are stateless. In order to make the trick, cloud providers treat stateful functions as stateless by keeping the state in some storage system in the same data center, which, by the way, is also built to the clients who pay once for the serverless service and another for the distributed storage system. However, in the edge, there is no such an easy way out, because it's non-trivial to implement a distributed storage system, and there is not a single entry point for the users, which are as distributed as the compute resources. Let us assume that we have a function which is not stateless, so which has a state S. For instance, let's assume that this function is able to predict whether maintenance is needed for a given equipment based on the input, which can be new samples acquired from a sensor, and the previous state, so all the samples that have been accumulated in a given time window, for instance. Also, the state has to be updated because the new samples have to go into the new state after the function has been executed. So in the cloud, top part of the diagram, what we do is that the application invokes only with the new samples the function f. The function, the container which is hosting the function, retrieves the state s from a storage system. It performs the computation based on x and s, and then it returns back the result to the client as y, and the updated state as s prime to the distributed storage system. What we propose to make this implementable on an edge network is that the application, so the client, keeps its state. So when it invokes the function f, it passes both x, the new input value, and the state to the function, which now has all it needs to perform the computation, and it returns both the result y to the client and the updated state as prime. This pattern can also be extended to the general case when an application is composed by multiple functions which are called from one another, which is very typical in serverless computing in the cloud. In this case, for instance, we have an application which is composed by 4 functions, F1, F2, F3, and F4. F2 requires a piece of state called SB, while F1 and F3 require a state called SA. So the notation is a bit redundant maybe, but I think the point is quite clear. So when you have an input X from the client, it has to go first into F1, which also uses SA, then it goes into F2, which uses SB, then it goes to F3, which uses the updated version of SA, then it goes to F4, which doesn't use any state in this example. And then the final result is returned to the caller. We have mapped our proposal a couple of slides ago in a straightforward manner to the function composition as follows. So let's keep in mind the example function composition from the previous slide, which is also shown in the upper left part of the screen. And then let's assume that we want to execute F1 and F4 on edge node 1, F2 on edge node 3, and F3 on edge node 2. Then what we need to do is that the client invokes with the input X, F1 on edge node 1, also passing a state A, and it gets back the output Y1 in addition to A prime, so the updated state of SA. And then it continues towards edge node 3, then 2, then 1, each time invoking a different function and passing the piece of state that will be needed by the given function. In the paper, we call this approach pure function as a service, because we can keep the same function as a service principle of keeping the function stateless by fully embedding the state as input argument and return value. However, if we look close enough to this sequence diagram, we can spot a possible source of inefficiency, which we might want to optimize out. So when the client executes the function F1, it has to wait for the result from the container on edge node 1, and then it invokes function F2 and it gets back the result, etc. Wouldn't it be better if the client could invoke just once the sequence of function, and then each head node invoked the next one autonomously, which, by the way, is something which is already possible in today's serverless systems in cloud computing platforms. We have implemented this pattern exactly as a state prop, or state propagation, as we call it in the paper, which also gives the name to the paper actually. In this approach, the client invokes only the first function in the chain, F1, including both the input parameters and the full state of the application, which in our example is SA plus SB. Then the full set of states is passed along together with the output of each function as an input of the next function as the function arguments. So edge node 1 invokes directly function F2 on edge node 3, passing also SA prime because it has been modified, and SB. Edge node 3 invokes F3, which invokes F4, which gets back the result to the client, together with the updated SA double prime and SB prime. And from the point of view of the number of functions to be invoked, we can be pretty happy because we have reduced significantly the number of invocations with respect to the pure FaaS approach described 1 minute ago. However, there is another source of inefficiency in this approach. We have to embed the state and carry it along the full chain also for the functions which do not use that state. So for instance, if we look to F4, it receives the full state SA double prime and SB prime without doing nothing to it, just is passing along the data. In order to reduce this inefficiency, we have proposed a third and last approach described in the paper and called state local. With this approach, you only pass along the input arguments of the functions from one edge node to another. And then if the function called actually needs a given piece of state, it can request it from the previous owner. So when F1 is invoked by the client, since it needs SA, it requests it from the client. After the edge node 1 has got the state SA, it does the computation and it keeps the state. So the new owner of SA now is edge node 1. The same happens for the state SB, which becomes owned by edge node 3 after F2 invocation. Then when function F3 is invoked by edge node 2, it requests the state from edge node 1, which invalidates the state on edge node 1, and edge node 2 becomes the new owner of the newly modified SA double prime. On the other hand, function F4 on edge node 1 does not request or modify any state, since it is, as a matter of fact, truly stateless. A small recap. So we have proposed in our work that in an edge network, the state of an application should remain in the network, which may mean in the client or in the edge nodes which make the edge network itself. We have proposed 3 ways to do so. So by using a pure function as a service approach, where the client performs function invocation in turn for every function in the chain of invocations needed by the service. We have proposed a state propagation approach, where the client only invokes once the function together with the full state of the application, which is passed along all the invokers until the client gets back the result. And finally, a state local approach, where the state is kept by the edge nodes. In order to understand the respective trade-offs between the different approaches proposed, in our research, we have used performance evaluation using simulation. For the performance evaluation, we needed two basic ingredients. One is the topology of the network under test. So for this, we have used the edge topology synthesizer, Ether, which can produce realistic topologies with some characteristics that mimic scenarios for urban sensing IoT or industrial manufacturing. This is, for instance, a possible snapshot produced by the synthesizer in the case of industrial IoT. On the other hand, we needed a way to generate our workload. For this, we have used SPAR, which is a generator of cluster traces, which has been tuned based on the traces made available publicly by Alibaba for their cloud jobs. SPAR produces applications in the form of directed acyclic graphs, DAGs, like the one shown in the slides. Actually, what we need is a chain of function invocations with some state. So what we did is we transformed those DAGs as follows. First, we have identified in the DAG what is the longest chain of function invocations. And this, for us, has become the chain of invocations. Then for the remaining tasks, the one in orange in the picture, we have transformed them into state dependencies. So those 4 tasks have become 4 states in the new transformed chain of function invocations. Then we have applied a typical Monte Carlo simulation approach. So we generate the topology and the workload, and then we simulate many drops where tasks are selected at random. We do the allocation of tasks or functions to the edge nodes using shortest job first, which is a very well known algorithm that is used in many online schedulers for multi-server systems. All the source code, the scripts, and the artifacts are available in a GitHub repository, which you are very welcome to try. In this graph, we plot a high percentile of the network latency for the 3 approaches proposed as the load increases. So we can see that the latency due to network transmission is highest with the pure FaaS approach. It is intermediate with state propagation, and as expected, it is lowest with the state local. This is due mostly to the network traffic that is generated by each different approach, which is plotted in this slide. In the previous plots, we have shown the results aggregated for all the functions invoked in a given batch. However, not all functions have the same size in terms of number of functions that are invoked in our workload. We can see that the state local curve is low and rather stable, which means that even for very long services, that is those services that have many functions invoked from one another, the network latency remains under control. While on the other hand, this does not happen for both state propagation and the pure FaaS. We are at the end of the presentation. Before you go, just a few takeaways. So serverless or FaaS is a fast-growing technology that we cannot ignore, and we definitely want to use also in edge networks. However, FaaS implies a statelessness. However, not all functions are stateless by their nature. Rather, very few are stateless. The traditional way, the cloud way of handling a stateful function does not work well at the edge. So we need new solutions. And this problem is exacerbated when you have a chain of function invocations rather than a single function invocation. For these reasons, we propose to keep the state of the functions at the edge, so in the network. We have defined 3 approaches to do so. One where the state is embedded into the function arguments and the return value. Another one where the state propagates from the initial function call until the client gets back the final result. And the last one where the state is stored by the intermediate edge nodes. And this one has performed best in our initial simulation results. Thank you for having stayed with me for the last 20 minutes. I wish you a nice continuation of the SmartComp conference. Goodbye.